All right, welcome to another video of Chem with Com, and we're going to do part 3 of 4 for the chemical equations and chemical reactions. All right, this specific one is precipitation and acid-base reactions. So here we go. All right, we're going to start looking at different types of reactions, and we're classifying them into these 3 specific ones, right? There's going to be precipitation reactions. And we talked about that a little last section, where 2 solutions mixed together create a solid, kind of the opposite of dissolving. Acid-base reactions, combining acid and a base to make water and a quote-unquote salt. This is going to be in the next lecture, but I'm just listing them here. It's total to keep track of them. Oxidation-reduction reactions, also known as redox reaction, where there's actually a transfer of electrons. And so we'll have to keep track of that as well. All right, so 3 different ones: precipitation, acid base, and oxidation reaction. Oxidation-reduction reaction. All right, precipitation reactions, we're going to combine 2 solutions that are clear. That means those are both aqueous dissolved solutions in the formation of a solid, right? And then your solid starts forming. It could be different colors. It can get cloudy. It can get really dense. It'll fall to the bottom, right? It's the opposite of dissolving. Most are ionic reactions, like we just talked about, the ionic rearrangements, right? We swap the cations. Um, Usually from double replacement reactions. So it's something like this where you have reactant AB, reactant CD, making you're going to swap the cations, right? That's typically what it did in the last one. And basically what happens is takes the place of C, so it's AD now, and CB are the thing. And what happens is one of those likes to form a solid, and it falls out of solution and it gets cloudy and it makes that precipitate, right? All right. So let's take an example here. Here, there's a clear solution of lead nitrate. They're both aqueous. So hovering around in there is lead. Um, Actually, yeah, I'm going to cover this next, but precipitation reaction, right? We have lead 2 nitrate in 1, which is a dissolved. They're both aqueous. That means they're actually separate and dissolved in there. That's aqueous, and then NO3. All right, I don't want to put the brackets there. NO3, 1 minus, aqueous. Those are floating around there. Potassium iodide's floating around here, 1 plus, aqueous, I, 1 minus, aqueous, right? Cool. They're not dissolving because they don't like each other and they're cool. But once that drop enters, right, now all these 4 ions are all together, these and these. Now something happens. Lead and iodine are compatible to make a solid. So it formed a solid. It changes the color. There's a precipitate, and we still have these potassium nitrate ions floating around. And these are remember those are called spectator ions, right? Because they're not participating in the reaction. All right, let's take a little closer. Boom. Lead nitrate, aqueous, means these are separate and dissolved in water. So you have lead floating around, lead 2 specifically, and nitrate floating around. They're just bouncing around, not doing anything. Here you have in the bottom part of the tube, you have potassium iodide. Also aqueous means they are separate and dissolved in water. They're just floating around. So, one of the things you want to do is you want to take your ingredients, you want to swap the cations and make new formulas. And experimentally, what you're doing is in a lab, you're combining these 2 things and you're saying, hey, did I see a color change? Was there gas formed? Was there energy transferred? Was there precipitate or color? I don't know if I said that already, right? But if there are, it means there was a chemical reaction. And if there was a chemical reaction, we have to rearrange the atoms because that's what constitutes a chemical reaction is an atom rearrangement. So uh, when we drop that stuff in, that lead 2 nitrate, it can now combine with the potassium iodide because all of these are in the tube together now. As soon as those two aqueous solutions touch, those are all now floating around. And what happens is lead and iodide come together and they form a solid. And that's that yellow right here. Potassium and nitrate are still just floating around doing nothing. Absolutely nothing, right? So again, experimentally, we see indication of a color change, so we have to rearrange the atoms because that's the only way it can happen. A chemical reaction is an atom rearrangement, right? So one easy way to do that is you just swap the cations. We're going to break it apart into, remember those total ionic equations? So we're going to break apart the ionic things. We're going to take a guess, hey, these didn't have a chemical reaction by itself. These didn't have a chemical reaction by itself. So they must be reacting with each other to form this yellow precipitate. And sure enough, it does. Right? And there's a cool video. If you Google lead iodide precipitating on YouTube, you can see it cool. This is like where I got the screenshots from. All right. So swap cations, and then we get potassium nitrate and lead 2 iodide. All right, so let's take a closer look. So how do we know what becomes solid? Well, experimentally. But before we do experimentally, or after whoever did this experimentally, they came up with they made a cool table that tells us what is soluble, what dissolves, and what is insoluble, makes solid. So let's say makes solids and then stays dissolved. All right, let's take a look. All these are soluble in water. But what happens is when some of these ions, so let's read these off. Ammonium, lithium, sodium, potassium, rubidium, cesium, right? They're always going to be soluble, and this is a table of exceptions, this line here. There's no exceptions. They're always soluble no matter what, right? Now what happens is these are usually insoluble. Sorry, usually soluble, except when paired with these. So if you have silver chloride, that's going to be a solid. If you have lead, like we just saw, lead iodide, that's going to be a solid. If you have mercury, looks like bromide, that's going to be a solid, right? Any of these three paired with any of these three will form a solid. All right, so typically chlorine, bromine, and iodine, those are all soluble, right? Okay. So fluorine, usually soluble, except when grouped with group 2 metal cations. So group 2 is the second row. So like beryllium, magnesium, calcium, things like that. Lead 2 and iron 3, right? So again, usually soluble except these guys. Acetate, this is acetate ion. This is bicarbonate, nitrate, and I think this is chlorate. Perchlorate? Yeah, chlorate. There are no exceptions, always soluble. Always soluble. These are always soluble. All right. Another exception is sulfate. If sulfate's usually soluble except when it gets paired up with these guys. Silver, barium, calcium. This is mercury 1, lead 2, strontium. Right? So again, the table on the left is usually soluble. These ones are always soluble. Always, always. Right? These ones here, usually. Except, and they're the exceptions. On the right side, right? These are always insoluble. And then group 1 cations are here, right? These group 1 cations. So basically, they're always insoluble. The exception is if it's paired up with any of these, right? And barium, sorry, barium, and this one is ammonium. So yeah, we'll reference this table later, and we'll come back to this. But again, what you're going to do is you're going to break apart these ions. If there's a chemical reaction, break apart the ions, aqueous ions, swap cations, and then you're going to check the table to see if it precipitates or not, right? So here you go. Break apart compounds in the reactants into cations and anions. Swap the cations with each other, make neutral compounds in the products, balance atoms, and then you're going to check the solubility table. All right. Potassium sulfate and barium nitrate. I knew that because of the charges. Step 1, you want to break those apart. So we broke those apart, potassium and sulfate, barium and nitrate. Right? And I forgot a 2 here. Let me just fix that real quick. All right, we fixed that. So we need to make sure it was balanced, right? Okay, so we're gonna break apart break apart all the aqueous stuff. Then we're gonna swap cations, right? The cations are the positive ones. And we're gonna make neutral compounds. Ba started out as 2 plus, sulfate is 2 minus, potassium is 1 plus, nitrate is 1 minus, so it's 1 and 1, 1 and 1. So we're almost done. Here, right, we swapped cations. We needed 2 potassiums because it's potassium 1 plus, sulfate 2 minus. We needed 2 potassiums, 1 sulfate. Here we needed 2 nitrates, 1 sulfate. So again, neutral compounds is a key part to this. That's why I've been emphasizing it all semester. Then you want to balance. The only thing that we need to do to balance is add that 2. So now everything's balanced. Then we check the solubility table, right? So let's check barium. Let's check potassium nitrate first, because I know that's not going to precipitate, right? Let's look at potassium. They say there's no exceptions. Always soluble, always soluble. So that's going to be aqueous. Aqueous, aqueous, aqueous. All right, let's check out barium sulfate. All right. Soluble. They say sulfate is usually soluble except when paired up with these. All right, well, we see barium there, so we know that's going to be a solid. So that's why barium is a solid here. So this is our precipitation reaction here. Right? Let me tell you one thing here. The reason why these don't get together, or not the reason why, but because this is aqueous, we know that these aren't ever going to get together. They're never going to bind. They're never going to bind, never going to bind. So we have to check the other combination. The other combination is this potassium and this nitrate. Well, we checked it on the table. Nothing happened. The other combination that can happen is this sulfate and barium. And we check that on the table, and that can become a solid. All right. So let's now try another one on our own. Oh wait, is this the same one we did? No. Let's try this. And actually, this one just asks for the basics. So let's just do the basics of the ask for, and then we'll do a more complicated one in the next example. Let me just make sure. Yeah, I think it's just asking to do if it's soluble or not. So let's do that. All right, so we don't need to build those giant equations, but which solution could be used to precipitate the barium ion? Precipitate means turn it into a solid with something else. In a water sample, so we have sodium chloride, aqueous. We have sodium hydroxide, aqueous, or sodium sulfate aqueous. All right. When we break these apart, they break apart into sodium 1 plus aqueous, and then chlorine 1 minus aqueous. So it breaks apart into same sodium 1 plus aqueous, hydroxide 1 minus aqueous. Then this one breaks apart into sodium, same thing, 1 plus aqueous, and sulfate, SO4 2 minus aqueous. Now check this out. Barium, what charge is barium? Well, it's a plus. Pluses will not bind to any other plus, so we can already rule out sodium because sodium is positively charged. You can't bond to barium. Sodium is positively charged. You can't bond to barium. This cannot bond to barium. Right? So we rule those out. So all we're going to do now is look at these and if it's compatible with barium as to make a solid. Right? So let's look at this. Chlorine here, usually soluble. Only exceptions are silver, mercury 1, and lead. Barium's none of those. So we'll say this is aqueous, right? So we'll say Ba, and then we need Cl2. This is aqueous. All right. Hydroxide. Let's find hydroxide on here. Well, it's usually soluble, except, so usually insoluble, means usually solid, precipitated, insoluble, except when it's with barium. So exception. We'll say soluble. So it's going to be BaOH, and we need 2 hydroxides, and that's going to be aqueous, right? It did not form a solid or a precipitate. Now let's check this last one. SO4 2 minus. Usually soluble, usually aqueous, except, look at this, barium. So because it does not, there's an exception for this one. It's BaSO4. This is going to be, oh, sorry. It's going to be a solid. Right? So this is the one that forms the solid. And the reason why we knew that, again, is because they're asking about barium. You're saying, hey, barium's here. Can it form a solid? Well, it cannot with sodium chloride because barium chloride is aqueous. Sodium hydroxide, barium hydroxide is aqueous, but barium sulfate is not aqueous. It is a solid. So this is where it will form a precipitate here. And the formula is, like we just did, BaSO4 solid. All right, let's check another one. Precipitating reactions, predicting precipitation reactions. Predict the result of mixing reasonably concentrated solutions of the following ionic compounds. Let's build these. Potassium. So K is 1 plus. Sulfate is SO4 2 minus. Barium is 2 plus. Nitrate is NO3 1 minus. So K2SO4. And these are solutions. So if they're solutions, they are aqueous. Plus Ba parentheses NO3 2, because we have a 2 plus charge here and a 1 minus. We need to make neutral compounds. We know they're aqueous because they are solutions. Here's where it might get a little funky, right? We have to swap cations. Let's swap them. So then this becomes KNO3 plus, we'll do the phases last, barium sulfate. Let's balance this. The only thing you need to do to balance this is that, and we're done. Let's check potassium nitrate. Well, potassium and nitrate have no exceptions. They're always soluble, so this is going to be aqueous. Barium, so with sulfate, it does make a precipitate with barium, because again, this little box are all things that are soluble. The exception is barium and sulfate, because those are incompatible or compatible for precipitation or solids. So there's going to be a solid. All right. And it says do the net ionic equation for this reaction. So we'll break apart the aqueous. So it becomes 2K1 plus aqueous plus SO4 2 minus aqueous plus barium 2 plus aqueous plus, there's 2 now, 2NO3 1 minus aqueous. We do that. We say 2 potassium 1 plus aqueous plus 2NO3 1 minus aqueous plus, this is a solid, it stays together. BaSO4 solid. Let's find the stuff that's the same on both sides. This is the same spectator ion, spectator ion, spectator ion, spectator ion. This is the only stuff that's left. Typically, you write the cation first, barium 2 plus, aqueous. And then we have SO4 2 minus aqueous. That makes barium sulfite solid. This is the net ionic equation. All right, silver acetate and lithium chloride. All right, let's do these here. Let's do B. So this was A. It's going to draw an arrow there. This is B now. Lithium, that's a 1 plus. Chloride is a 1 minus. This is a 1 plus. This is a 1 minus. So it's going to be just a even swap. So lithium chloride. Let me just see if there's another. Lithium chloride, 1 and 1. And they say those are aqueous solutions. plus silver acetate. So silver and then acetate's kind of this one here. So it's C2H3O2. Again, that's aqueous. Let's swap cations. And then let's draw the new ones. So since they're all 1 plus 1 minus, it's just going to continue. So lithium, C2H3O2. We don't know the phase. And then silver chloride. All right. We don't know the phase. Well, it's already balanced, but let's check this out. Anything with lithium is aqueous. Anything with acetate is aqueous, so this is going to be aqueous. Chloride, let's find it. Well, it usually is soluble, so usually aqueous, but when it finds silver, it is now a solid. Okay, well, now we got to break everything apart. I'm just gonna, oops, sorry. I'm gonna break all the ions apart. Let me just move this stuff out the way so we can see better. All right, so lithium, I'm gonna draw it a little higher because I'm running out of room. But lithium, 1 plus aqueous, plus chlorine, 1 minus aqueous, plus silver, 1 plus aqueous, plus acetate, 1 minus aqueous, makes lithium, 1 plus aqueous, plus acetate, 1 minus aqueous, plus as this is solid, stays together. Cl solid. All right. Box up the, let me erase this just so we can see what we can cancel that. All right. We're going to box up the stuff that's the same on both sides. So lithium and acetate. We're going to leave those out because those are the spectator ions. So it's just going to be Ag, 1 plus aqueous, plus Cl, 1 minus aqueous, makes silver chloride solid. So this again, this is the net ionic equation. You can see it's a lot less stuff going on because it's just the ions that are doing something. All right, let's do another practice problem, our final one, and then we'll get into other stuff. Okay, so we're going to do the last example here. It's going to be lead to nitrate and ammonium carbonate. All right, I'm going to label these lead to nitrate, ammonium NH4 1 plus, carbonate CO3 2 minus. Again, those are polyatomics. The lead's not, but you should be used to those by now. If not, go take a review in the nomenclature chapter. It's going to help you a lot with this. All right. Lead to nitrate. So we need 2 nitrates, PbNO3 2 aqueous plus ammonium carbonate. We need now 2 ammonium, so it looks like this, because we need 2 and then carbonate. And this is supposed to be aqueous. All right, swap cations. We're going to make this, let me move this to the side a bit. All right, swap cations. So it's going to be, what do we want to do here? Let's do ammonium and nitrate. Neutral compounds, 1 and 1. We don't know what this is going to be. I kind of do because I can see the chart right here. But we're going to do now the other one, which is lead 2 and carbonate. All right. We don't know what the phase is either. So we have to balance this. We need 2 ammoniums, 2 nitrates. We are done. Just that 2 there. All right, so now we're going to check the table and see what happens. So ammonium and nitrate, always soluble, so aqueous. Lead carbonate, usually insoluble. The only exception is ammonium and anything from group 1, which is these. So that's going to be our solid. All right, break apart aqueous. Pb, 2 plus aqueous, plus 2NO3, 1 minus aqueous, plus 2NH4, 1 plus aqueous, plus CO3, 2 minus aqueous. All right. Now we have 2 ammoniums, NH4, 1 plus aqueous, plus 2 nitrates, 1 minus aqueous, plus now solid, we don't break apart, lead carbonate. Sounds like carbonara. I think I'm hungry. All right. Box up all the stuff that's the same on both sides with a different color. So nitrates are the same on both sides. It has to have the same number, the same charge, the same state, everything, right? So we can't just box up things that are similar. They have to be exactly the same. So let's write this out. Everything that's left over, this is going to be our net ionic equation. Pb, 2 plus aqueous, plus CO3, 2 minus aqueous makes lead carbonate, or carbonara, whatever you're thinking about, right? This is our net ionic equation. The stuff boxed up in blue are our spectator ions. They don't do anything. We just put the stuff that actually has some action going on, right? All right. Acid-base reactions. What makes something an acid? We reviewed this in nomenclature chapter, but it can release a hydrogen into water. So HCl, since it's aqueous, it's in water, boom, it came off. That's now an acid. H2SO4, aqueous, that means it's an acid because it can release those hydrogens. Bases accept a hydrogen. They can take a hydrogen. So if you look here, this hydroxide, this OH, which is a water, it was actually able to take that hydrogen, and now it's H2O. This carbonate was able to take 2 hydrogens to make it H2CO3, which is hydrogen carbonate or carbonic acid, right? Acids usually start with an H in the formula, which we did. Product is usually water. Check this out. Oh, actually, no, we don't have any things up here, but the most common bases are hydroxide and carbonate. You find these in antacids for your stomach, but there are many other bases, right? So, but we're just going to use these as our main examples to not get crazy. All right. Acid-base reactions. Let's do the same thing we just did. Write the net ionic equation representing the neutralization of any strong acid with an ionic hydroxide. So these are all ionic hydroxide. Those are bases. So let's take a look. All right. So let's just pick one. Doesn't matter which one. Let's do I think we've done sulfuric acid a few times, right? Let's do something else. Let's see, we did. Actually, no, it's no acids. Let's just pick whatever then. Let's do sulfuric acid just because it has 2 hydrogens. I like using those. Let's do sulfuric acid and let's do. I don't think we've done lithium hydroxide. Let's do that one. All right. So hydrogen in the front, we're expecting this base to accept the hydrogen and probably that hydroxide. I'm assuming that's what it's going to be. Let's do it. 2SO4 aqueous plus LiOH aqueous. Swap cations. It becomes lithium 2 sulfate. Not lithium 2, sorry. Lithium sulfate, sorry. We know anything with lithium is going to be aqueous, just because we knew that on the last, or the table here, right? Anything with lithium's aqueous. What's the other thing? What's H, O, and H? That's water. So because we have an acid and base and water, we know this is an acid-base reaction. We have to balance it. Let's balance the sucker. So we need 2 lithiums here, right? Because we have 2 lithiums here. 1 sulfate, 1 sulfate. Now we have 4 hydrogens. 1, 2, 3, 4, and 2 oxygens. So 4 hydrogens, 2 oxygens. That looks like 2 waters. So now we're done. Separate everything that's aqueous. That's what we're doing next. So I'm gonna come down here a little bit. So we have 2H1 plus aqueous plus SO4 2 minus aqueous plus 2 lithium 1 plus aqueous plus 2OH1 minus aqueous. Arrow, we have 2 lithiums, 2 Li 1 plus aqueous plus SO4 2 minus aqueous, and then we have these 2 waters. So 2H2O liquid. Box up stuff that's the same. Hydrogen. Oh, sorry, there's no hydrogen there, so it's not the same. Cancel that. All right, let's check sulfate. Sulfate is the same. Sulfate is the same. We'll leave those out. Lithium is the same. Let's leave those out. All right, so then we're going to use our leftovers. It's going to be 2H1 plus aqueous plus 2OH1 minus aqueous makes 2H2O liquid. But we're going to cancel these 2's and just say H1 plus aqueous plus OH1 minus aqueous make H2O liquid. And that's the net ionic equation for an acid-base reaction. Most of the time, right? Sometimes it's a little funkier because it's not water, or so it's not hydroxide. All right. Well, that's it. Thank you very much, and I will catch you next time. If I can get out of here.